All right, thanks, Paco. Hi, so my name is Richard. I'm a software engineer and team lead at Anyscale, which is a startup working to democratize, democratize distributed computing and commercialize Ray. Previously, I was a PhD student at UC Berkeley working on machine learning systems and cloud computing. Um, During my PhD, I primarily worked on building out Ray and Ray 2, which are distributed computing libraries targeting AI applications and hyperparameter tuning. So today I'll be talking to you specifically about sort of the bigger, broader context of hyperparameter tuning and deeper, providing a deeper dive into the Ray system. So for this talk, just as a quick outline, we'll begin by motivating the importance and highlighting the complexity of tuning model hyperparameters. Then we'll overview some of the state-of-the-art techniques for optimizing hyperparameters. And finally, I'll talk about RayTune, which is a Python library for simplifying and scaling hyperparameter tuning. At the end of this talk, you should be able to leverage new algorithms and new frameworks to accelerate your machine learning workflow. So let's begin with some context about machine learning today. Machine learning, specifically deep learning, is experiencing rapid growth and adoption. And this is not only happening in academia, but also in industry, where more and more applications such as speech recognition or autonomous vehicles are leveraging deep learning. Despite this rapid growth and adoption, all deep learning practitioners actually know about this dirty secret. There's one particular dirty secret, and that's the need and reliance on hyperparameter tuning. Now, if you don't believe me, let's give an example. Let's quickly talk about convolutional neural networks. Convolutional neural networks are very powerful, and they're attributed to many of the recent advances in computer vision. On the screen, we have one of the original convolutional neural network designs by Kuhn. Now, on the bottom, we have AlexNet, which was, it was developed 20 years later after the original CNN, and it's actually brought about a large wave of new deep learning research that we see today all across the world. Now, what's interesting about these two figures is that the basic idea of convolutional neural networks have remained largely unchanged. Over the last 20 years, besides increasing the availability of computational resources, we've only largely modified the shape of the neural network and the size of each layers. And these are typical things that you might call hyperparameters. And turns out these hyperparameters can make a huge difference in performance. And what's making matters worse, especially nowadays, is two trends. We see the first trend is that we see that models are getting larger and larger, with the most recent OpenAI GPT-3 model containing nearly 200 billion parameters. Second, these state-of-the-art models are not only larger, but they're also more complex. On the screen, we have the hyperparameters for a simpler speech model called Roberta, but it also has dozens of hyperparameters. So this means that selecting the right hyperparameters is simply going to start taking a long time and consume a lot of resources in order to get sort of a cutting edge model for your own practical deployment. So now that we have all this context, we arrive at the main problem of hyperparameter tuning today, which is that it's not simply just how do we choose these hyperparameters, but how do we choose them both efficiently and quickly? And we can address this problem with a two-pronged approach. First, we can leverage advanced algorithms to navigate the optimization, the search space of different parameters given. Second, we can use cutting-edge software to better leverage our compute resources. And I'll be talking specifically for leveraging compute resources and cutting-edge software. I'll be talking about RayTune, which is a library for scaling hyperparameter tuning. Today, we'll cover 5 types of tuning techniques. We'll cover grid search, random search, Bayesian optimization. These are typical things that you've heard of. We'll cover HyperBand or bandit-based techniques, which you might have already heard about from a previous talk. And then we'll also cover population-based training, which has more of a significance in the deep learning regime. So one keynote here is that I'll be using the word trial very often. You can imagine that when you do a hyperparameter search, you evaluate many different hyperparameter configurations, and each one of these configurations I'm going to call a trial. So in summary, multiple trials consist of or compose into a hyperparameter tuning experiment. So let's first start with the grid search. This is a very typical and standard technique for evaluating multiple hyperparameter values. What you do is you take a list of values for each different hyperparameter that, for example, like learning rate, the number of layers in your neural network, or an arbitrary parameter configuration. And what you do is you just take the cross product of all the items in each list. So this may seem very naive, but it's actually, first of all, very often used. Many of the standard research papers nowadays still use this technique. And the reason is because there's a couple benefits. First is that it's easily parallelizable. Second is that it provides you insight into how your hyperparameters can affect each other. It's a very structured, controlled execution. Now, the problem is that if you're simply trying to optimize in order to get the best score or accuracy, grid search is not very efficient. And so let's take, for example, a grid search on the screen right here. The sort of intuition why grid search may not be very efficient is because if you look on the left-hand side, on the very top of the square, you might be plotting the accuracy over the grid. And it turns out that the grid evaluation points simply miss the most important part of the optimization landscape. On the other hand, if you take a look at random search, the random search is able to provide a coverage of the landscape, which is really important, especially when there's a certain one parameter that is more important than the others. So for example, here, the x-axis is much more important and clearly indicates that there's a part that correlates with the best performance. Random search is able to provide a better sense of coverage over that same landscape than compared to grid search. So to quickly walk over example of random search, it's exactly what it sounds like. Given different distributions, so it could be like normal distributions or uniform distributions for each hyperparameter value, you sample parameters from each of these distributions over and over again, ultimately finding the best model. Similarly to grid search, the benefit of random search is that it's easily parallelizable. Each evaluation, each trial is independent of each other. And actually, in very high dimensions, it's certainly very, very hard to beat. And the reason is because other methods sort of just break down when the dimensionality becomes too large. But there's actually a couple things that make random search preferable. Well, obviously, compared to grid search, it's much harder to draw correlations and have a structured analysis. But often, actually, another thing is that you're often trying things. You're obviously trying things at random. So one question is, okay, well, let's assume we have some sort of like nice landscape. What if we used some prior information from evaluated training runs to guide the search process? Well, this is typically what you might do, what you might call Bayesian optimization, and just more generally, what you might call a model-based optimization process. So here's a very high-level overview of Bayesian optimization. Without diving into too many details, we construct an optimizer that's aware of the search space. So if you look at the code on the screen, there's like a learning rate, and there's layers, and there's a bound. There's an upper range and a lower range. And the optimizer is just going to sort of try to find the optimal point within these bounds. So we'll sample from this optimizer to get 1 point. We will train the model, right? We'll train the model to get a final score, such as accuracy or a loss. Then we'll take that score and we'll pass it back into the optimizer, and the optimizer will use that information to generate a new point to sample. Ultimately, it will aim to optimize the given score. And there's a lot of open source libraries that do this. Most famously, you might hear of Optuna or HyperOpt. They're essentially libraries for Bayesian optimization. Now, as you can see, Bayesian optimization is an inherently sequential process. It utilizes prior information, but it is to actually some extent parallelizable. You can actually sample multiple points at once, but again, the parallelization decreases significantly as you add more workers. So now that we kind of have the three big sort of table stakes of hyperparameter tuning on the board, let's take a look at how we can actually do better. So if you take a look at this graph of training accuracies, there's a lot of models that are simply just bad for performers. So you might naturally just ask, well, why bother wasting resources on trials that are simply not going to be good? And there's a hyperparameter tuning technique that addresses this precisely. So VM is here, but this is one of the most standard techniques that we use in industry today, and it is invented by or contributed significantly by VM, who gave a talk earlier today. So HyperBand is a early stopping algorithm that aims to allocate resources to better performing trials. So let's quickly walk through some pseudocode. So we start with a hyperparameter space as we had before. We sample from it and we get one trial, and we will evaluate this trial iteratively. So we will train it one epoch at a time. At the cutoff, so there's a specific value that we will train it for, some number of epochs that we'll set ahead of time. And this might be something very small, something like 1 or 2 epochs. Now, what we will do is we will run this trial until that cutoff. And if this one trial is in the top fraction of all trials, so it's one of the better performers, then we can extend the cutoff. We can let it run for longer. Otherwise, we will pause it and we'll let some other trials to be evaluated. Essentially, this encodes this ability to continue the better trials, to allocate more resources to the better trials for a longer period of time, while reducing the number of resources we allocate to poor performers. There's also been some recent advances that have made these bandit algorithms capable of being combined with Bayesian optimization. HyperBand is also easily parallelizable, which increases its efficiency. Finally, there's still room for some improvement. And turns out in deep learning, hyperparameter schedules can matter a lot. This means that the way we change, we might want to change a hyperparameter value such as learning rate or momentum during the course of training. And actually, many of the papers today almost certainly require this sort of behavior to occur in order to reproduce state-of-the-art performance. So there is one technique that we've seen over and over again that has seemed to work very well in capturing this behavior, and it's called population-based training. The main idea of population-based training is that you evaluate a number of trials in parallel. You'll terminate the lowest performers, but then what you'll do with those released workers or released compute resources is you'll mutate a best performer and copy the weights of a best performer onto those free workers. So essentially, you get to get the best of both worlds of being able to explore hyperparameter schedules in addition to terminating lowest performers. So let me quickly walk through an example. We'll start with a set of hyperparameters, say one hyperparameter for each trial, and you have something like 0.1, 0.2, 0.3, 0.4. After some number of epochs, you'll find that one of them performs very poorly. And so that happens to be 0.4. So what we'll do in population-based training is we'll terminate the lowest performing trial, and then we'll copy over the best performing trial, say it's like 0.1, and then we'll perturb its hyperparameters a little bit. So now it's 0.15. And we'll copy the weights over a little bit too. So effectively, we're exploring the hyperparameter schedule for starting at 0.1. And we'll do this again, and we'll find another trial that performs poorly, and we'll mutate a better performing trial, such as 0.3, and over again. Again, this is easily parallelizable. It allows you to search over schedules, and it's also efficient in that it terminates early bad performers. So obviously the question is like, well, does this really work? Well, when DeepMind published this technique, they ran this algorithm over existing published algorithms, so existing published papers. They found that across many different algorithms, they were able to provide non-trivial performance increases over the state of the art. And in our own personal experiments too, we found that population-based training has been able to even be extended to more modern models such as transformers and BERT. And we've been able to increase performance accuracies over these models for a variety of tasks. So now that we have a high-level overview of all the different hyperparameter tuning techniques that you might want to know about, I just want to give a couple quick tips for effective hyperparameter tuning. So the first tip I want to give is motivated by a blog post that I read earlier the other day. One of the authors brought up that what common pitfall for hyperparameter tuning is that practitioners weren't tuning enough parameters. In fact, they recommended that all practitioners tune all of the hyperparameters of the model at the same time. But actually, this is quite inefficient. And the reason is because there's dozens of hyperparameters that you can be tuning in modern machine learning models, but only a select few really matter, which means that most of them don't really do much, and most of the defaults are quite robust. And what this also means is that you want to effectively choose which hyperparameters you want to search over, and it's probably worth investigating and investing in those ones that are much more important, so to speak. So effectively, the high-level idea of this tip is that choosing the parameter space itself is a very important decision. Okay, well, you might be asking, well, how do I do that? The second tip I have for you sort of leads in from the first one is you should use available tools for visualizing and understanding your hyperparameter search landscape. A common, really useful tool is the parallel coordinates tool, which allows you to visualize n dimensions of parameters at once and also marginalize different results depending on whether or not you want to identify sort of correlations and responses between different hyperparameters. The nice thing about this technique is that it's actually available on most visualization libraries such as TensorBoard and weights and biases. Finally, I think one of a big pitfall that I see is that the hyperparameters chosen during the tuning process don't actually generalize really well. I think my tip here is that you should probably always remember that hyperparameter optimization is by definition an optimization process. And so the user and the practitioner should be really aware about providing nice, good, clean inputs into the optimizer. So you can do this by cross-validating your model during training, training across multiple seeds, looking at different metrics at the same time, in addition to just one simple metric or score. So ultimately, what you want to do is you want to denoise your optimization sort of evaluations so that you can do a better job optimizing, or that your optimizer, your Bayesian optimization, do a better job. So finally, I want to talk really quickly about RayTune, which is a scalable hyperparameter tuning library, which is essentially built to address all these problems that we mentioned before earlier in this talk. For some quick context, RayTune is a scalable hyperparameter tuning library built on top of Ray. Ray is both the framework for distributed Python, but also a ecosystem of libraries for specific use cases, including hyperparameter tuning, model serving, distributed reinforcement learning, and also distributed deep learning. So RayTune specifically handles the execution of hyperparameter search. It allows you to easily plug in different search algorithms while automatically handling the parallelism for you. Now, why is RayTune special? There's so many different hyperparameter tuning frameworks out there. Well, it's actually built, the one thing that we say is that it's built with deep learning as a priority. It allows you to effectively utilize and spread your training across multiple resources. It also allows users to tune models built with almost any machine learning framework. Finally, it allows you to run hyperparameter tuning at any scale, going from one process to a bunch of GPUs to running on multiple nodes, all without changing your code. So regarding all of the algorithms that we mentioned today, Tune offers everything that we covered, in addition to plenty of other open source hyperparameter search libraries, including Axe from Facebook, SigOpt has a wrapper, Scikit-optimize. These are all very common hyperparameter or common optimization libraries that you can just plug in with one line of code. And Tune will automatically, transparently scale these optimization processes across multiple cores and multiple nodes. So let's quickly walk through a demo of the API, given the last bit of time that we have left. So we can start off with a model training function. You've definitely seen this before. This is probably some pseudocode, but you're taking some model that you're configuring and you're calling train, and you get a loss. So all we need to do to use Tune is we can just simply import Tune and add Tune's reporting API to the training function, logging the loss. This is very similar. This is a simple line of code change, and that's all you need to do to effectively hook a function up into Tune. To run a search, now all you need to do is call tune.run. To perform a large-scale search, you can specify a search space and add an argument. The specific example that we have on the screen runs training the 100 different trials, and it will do this concurrently up to the number of cores in your cluster. You might want to leverage a GPU, and if you want to do that, typically you might have to handle ugly environment variables and manual device placement. With a single parameter, team will automatically set your environment variables and parallelize your search across multiple GPUs, even across a large multi-machine cluster. So through this very narrow API, Tune exposes a variety of other features such as automatic checkpointing, specifying tuning algorithms. And finally, as we mentioned before, it's very important to analyze your hyperparameter tuning runs. Tune automatically provides a data frame for you to analyze training results. And it also generates TensorBoard files so that you can visualize and understand your training with coordinate plots and scalar graphs. We also offer a lot of other integrations, including integrations with weights and biases. There's a new integration coming out for other experiment management tools, and so on and so forth. The high level here is that RayTune is here to make your life easier so that you don't need to do all this busy work yourself. If you're interested in learning more about RayTune, you can check out the documentation where you can find tutorials for using Tune, walkthroughs for integrating Tune with multiple different machine learning libraries, and many different examples for different features. And if you have any questions, you can also head over to our GitHub, where we have a large, thriving community and responsive developers that are more than happy to help you out. So now that we're at the end of this talk, essentially I want to sort of recap what we talked about today. In this talk, we motivated the importance and highlighted the complexity of hyperparameter tuning. We overviewed some state-of-the-art techniques for tuning hyperparameters. And finally, we talked about RayTune, a library built on top of Ray to simplify and scale tuning. Hopefully, this information presented will help accelerate your existing machine learning workflow. Finally, I just want to give a quick shout out. We have a really exciting free event called the Ray Summit. It's online. It's at the end of the month. And we'll be giving talks and large announcements about all sorts of different cool things that are happening in the Ray ecosystem. We'll also be giving talks about distributed applications and also machine learning applications of all kinds, including online learning, distributed training, so on and so forth. And there's a large, really exciting list of speakers that there's so many that I can't name off the top of my list, but they include sort of the maintainers of Hugging Face, maintainers of scikit-learn, etc. So definitely check this out, and you can head over to raysummit.org for more details. Now, I'm definitely, it was a great pleasure to be here. Thanks for listening. If you have any more questions, you can feel free to ask in the chat box above or reach out to me on Twitter or at my email. Thanks, everyone.
Thank you, Richard. That was excellent. We do have some questions. There's the Q&A tab. I will check also on Slack, but there's a few questions queued up under the Q&A tab.
Awesome. So I'll probably just go over these by a list of responses. So someone asks, is this open source? And yes, it is open source. It is available on GitHub. It's completely developed in a transparent way. You can head over to, it's called Ray. I think just head over to this like web page, tune.io, and then there should be GitHub link. So the first question is, how do you evaluate the accuracy of AutoML models? I guess there was a follow-up question that said in that same thread that was like, what are your recommendations for checking the accuracy for models? When should we go to AutoML compared to custom machine learning models? I think it depends on your use case. obviously one of the best ways to make sure that, I guess what you're actually asking here is that how do we know that the model that we are training is going to actually do really well in practice? And I think there you have to have really good practice, like good sort of procedures of making sure that you don't overfit on your training set, making sure you do cross validation correctly, um, making sure you hold out so you have some part of your data set that doesn't get evaluated. And ultimately, what you want to do is you want to make sure that the objectives that you're optimizing actually corresponds with the business logic or the business objective, and that's sort of up to you to sort of like make that decision. When should we go to AutoML? I think depends on your expertise. It's more like a practical suggestion. Like, if I was in a team of a bunch of people who didn't ever practice doing machine learning before, then I'd probably suggest AutoML as the first go-to solution. Alternatively, if your experts on your team are very well versed in machine learning, it's very likely that AutoML will be much more expensive than you need to than necessary, and you can probably quickly iterate on a custom model that does just as well. So another question is, in what order would you tune the most important hyperparameters? That's a good question. Obviously, like the learning rate, I think is the most important hyperparameter by far. Oh, these are great questions. Yeah, so learning rate is great. Momentum, these optimization parameters are generally like very important. But I think after you have a general set of like, I think learning rate is a great one, batch size is a great one, and then the rest you can sort of it's sort of problem dependent. You might want to let's see, it probably is a good idea to sort of, if you have sort of stages in your machine learning pipeline, like data processing, and then feature engineering, and then model tuning, you probably want to do step by step. So first, like, tune the best, get something working in your data processing there, then tune your features, then maybe tune your model a little bit more. And for the earlier in the stage, if something doesn't do that well, where you obviously need to have a pretty decent model ahead of time in order to sort of evaluate the goodness of the data processing stage. And so there might be some sort of iterative process here where you tune the pipeline once and then you go back and you sort of bootstrap yourself again. So ultimately, this is sort of problem dependent also. Another thing I would do is just like look at how people are doing this on like Kaggle or something like that, where people publish how they do this like processing of parameters and stages of the data science pipeline. How does hyperparameter define? I actually can't understand the first half of this question, but I can answer the second half, which is how do you choose the optimal hyperparameter for a specific model training? I think the answer here specifically should be just like it should obviously be the performance. Like you should obviously be tracking the performance of each model that you're training, each trial. And ideally what you're doing is you're going to evaluate a good number of hyperparameters, good enough to sort of find out which set of hyperparameters or which sort of a section of hyperparameter space is going to provide the best models. Obviously it's going to be very hard to find something optimal. So when we say optimal, it's most likely something that's near optimal or something that's like good enough. So another question was, can we use tune to tune other hyperparameters along with model optimization? I think this is what the question is asking, but of course, like you could let me know if I'm not interpreting this correctly. Obviously, yes, you can. So tune is sort of a black box optimizer. It evaluates and sort of sets resources for you. So if you want to tune something else like system parameters or like data processing parameters, that's totally possible. Final question, which was a great question, was does the pruning strategy hinder cross-validation? And so, yeah, so I think this is a great question. You have to be very careful about how you do pruning here. Obviously, if you prune at different, so if you have 5 cross-validation folds, and each model sort of is being very aggressively pruned, you end up with a score that's sort of all over the place. So one model might, by random seed, just perform really poorly and gets terminated before it learns anything. On the other hand, another model performs really well, and suddenly your spread of evaluations for cross-validation is like very large. So the solution here is simply to make sure that when you do cross-validation, you sort of do cross-validation before you prune. So what that means is like you might have one model, you're going to sort of train the model, or you can train like a basket of models on your cross-validation folds across training. And when you do pruning, you prune all the models at the same time. So basically you just have to be a little careful about how you do it. But if you do it in the right way, you should be able to do it without hindering cross-validation. This is a great question though. K-fold validation versus normal validation set. Which one do I find best? K-fold is probably better. But I mean, just because it's a little bit more like you can specify like 5 different folds, it's sort of like the standard that people also recommend. But obviously, like it could very well depend on your data set and your problem yourself. But personally, I would say like K-fold is probably what I would go to. I guess also another limitation of K-fold is that there's a lot of frameworks that don't actually support this really well. So just being cognizant of that, I think that's very, very important.